Okay, so we talked about the regeneration gas turbine, and we now learned that by having a regeneration gas turbine, we can improve the thermal efficiency. But you have to remember that by having a regeneration, it does not mean that we can increase the net work. Net work is still remains the same. We only try to reduce the heat input that results in the improvement of thermal efficiency. So let's take a look at this example to see how the regeneration can improve the efficiency. So now we are going to use the exactly same gas turbine as we tried to solve in example 28 in the last lecture. But first thing that we want to do is that let's assume that your compressor and turbine are not ideal anymore. So what it means is that in this example, we are given that the compressor efficiency or the isentropic efficiency of a compressor is 80%. And the turbine efficiency is 85%. So because of these irreversibilities, then our performance of gas turbine should be worse than the ideal case. Then in that case, can we really calculate the compressor exit temperature and turbine exit temperature? Obviously, these two values should be different because we are talking about different operational conditions. Now, what would be the back work ratio? And what would be the thermal efficiency? Then the next question is, what would happen if we decided to add a heat exchanger or regenerator to this gas turbine, and if this regenerator has the effectiveness of 80%, then what happens to the efficiency and work and so on? By looking at the TS diagram, we should have vertical line in 1 to 2 for the ideal Brayton cycle or ideal compressor. But because the compressor has the isentropic efficiency of 80%, your exit point should be different from this vertical line, but it should go more on to 2A in the increasing manner of the entropy. So in the case, let me just mark that as 2S. So same thing happens in the turbine. So in the turbine, the ideal turbine would make the exit condition to 3S, 4S, which is the vertical line in the TS diagram. But what happens in reality with the isentropic efficiency of a turbine, the exit condition makes it to the right side to increase the entropy. So that is what we see in the 4A condition. So with that being said, how can you calculate the exit temperature of the compressor and exit temperature of the turbine? What it means is that what is the temperature at 2A and what is the temperature at 4A. So 2A and 4A here. What we know is the equation of the compressor efficiency, which is given as 2S minus H1. Always remember the compressor work for the ideal case is smaller than the actual case. So that is what it can write it. Now, by assuming that your working fluid is the constant specific heat, or cold air standard assumption, what it can write is everything in terms of temperature. So now, okay, then we can cancel Cp. So the temperature at T to A can be written as this. Okay, now we know T1, we know eta C, but do we know T to S? So obviously from this the example statement, we don't know T to S, but we can calculate T to S because we know the process. In that case, the process is isentropic process, and we can use this equation. How can we describe the isentropic process when your working fluid is an ideal gas with constant specific heat? We already talked about it in the last lecture, and let me write that equation right away. Now, do you remember this equation? I hope you do. So from example 28 in the previous lecture, we already know T2 over P2 over P1, which is pressure ratio. We also know K value, and we also know T1. So we can calculate this T to S, right? So we can calculate T to A. Now, how about the turbine efficiency? So turbine efficiency can be written as this. Right? So we also still can cancel the CP out. So T for A can be written as this equation. And also we can calculate T for S with this equation. So we can calculate T for A. So because we now know T to A and T for A, we can also calculate the back work ratio, which is WC over WT, which can be written as enthalpy difference, or under the cold air standard assumption, we can write that way. And we already calculate these two values, and we know T1 and T3, so we can calculate the back work ratio. And how about thermal efficiency? Same thing, right? So we know this, and we know the net work can be written as WT minus WC, which is CP T3 minus T4A minus CP T2A minus T1, and Q in is CP T now T3 minus T2. So from this equation, the thermal efficiency can be written only in terms of temperatures, because CP are all there and CP can be cancelled out. So let me write that equation. Right? So we know all temperatures that we can calculate it. The last question is about the thermal efficiency for regenerator, regeneration gas turbine. So what it means is we still want to calculate Q in for regeneration. Okay, so because the thermal efficiency of regeneration can be written as net work, which doesn't change because there's nothing we have done on that compressor or turbine operation, but we have this equation. So the regenerated amount of the heat input for the regeneration can be calculated as CP now T3 minus T5, right? Because from the TS diagram, okay, we have T5 that is after regeneration from the air side. Okay, so the amount of heat input should be same as the enthalpy difference between 3 and 5. So that is what he can see. So we know T3, we know CP, right? We also calculated WNet, but how can you calculate this T5? We still don't know this T5 value. But one condition we haven't used so far is the effectiveness of regenerator. Again, the effectiveness of regenerator is defined as Q regenerated heat divided by the maximum generated heat from the air side. So what it means is that this Q is CP now T5 minus T2 divided by CP T4 minus T2. Okay, so in the case it should be T to A and 4, okay, and 4A, right? Because everything is in realistic actual values, and that is 0.8. And now we don't have CP, or CP are cancelled out. So from this equation, we know T5 explained in terms of all numbers that are given or we already calculated. So that is 764.9 Kelvin. So from this temperature, the heat input for regeneration can be calculated by, again, T3 minus T5. So that gives us 537.8 kilojoule per kilogram. Okay. So now the thermal efficiency of regeneration system is 0.356%. So in previous lecture, we did the ideal Brayton cycle analysis. Okay, and from this ideal Brayton cycle analysis, we calculated the power, and we also calculated the thermal efficiency, and we calculated the back-work ratio. And now in this present example, we also calculated these all values for the realistic actual gas turbine with isentropic efficiencies. Okay. Then we also assume that there is a regenerator attached. Then we also try to calculate the thermal efficiency for regeneration system. And now let me just pull all these values up, and then let's try to compare all these values together. So this is all results for the example 28 from the previous lecture, and now the realistic gas turbine. Now that's what we did, and even for the regeneration that is attached to the realistic gas turbine. Okay, let's not worry about T24 because they are not quite important at this moment. But if you really look at the back-work ratio, for the ideal case, we only need around 42% to run the compressor, but that is shoot up to around 61.5%. Okay, so what it means is that for this actual turbine, gas turbine, around 62% of the power that is generated by turbine should be used to run the compressor. Only around 38% is used as a net power. So that is a big loss, right? And as a result of these realistic features, the efficiency, the thermal efficiency, drops from 44.8% to 27.4%. So around 70% and more than 70% of the energy you get by burning out the fuel is being wasted without using it. So that is a big loss. Okay? But what happens if you have a regenerator? So by having a regenerator, the back-work ratio wouldn't change it. So basically it should be the same. And even though I didn't show you the net amount of work, that net amount of work for the realistic case doesn't change even though we have the regenerator. But what happens is the thermal efficiency. And as you see, there's a big boost up of the thermal efficiency from 27.4% to 35.6%. Okay? So that is exactly why we need sometimes a regenerator. Okay, and the sole purpose of having a regenerator is to improve the thermal efficiency.